Good morning, Astronomy 1020. Welcome to part 2 of our 12th lecture, where we will continue learning about the evolution of stars and the different types of fusion they undergo in their cores, and prepare ourselves for our next week's lecture, where we will get into the nitty-gritty of stellar death. That's when it's time for us to start talking about cool exotic objects like neutron stars and black holes. So we're leading up to the death of a star, where we can witness them become these strange and bizarre objects that are fun to talk about. Let's start off by talking about a one solar mass star. Okay, let's draw a picture of this before we continue working on that chart. So a star with the same mass as the sun. Today, it is undergoing hydrogen to helium fusion. And in the core of the sun, hydrogen is being converted to helium by what nuclear reaction sequence, my students? What's the name of the nuclear reaction sequence?
Proton-proton chain.
Beautiful, the proton-proton chain. And you will remember that in the proton-proton chain, let's see if I can get the slide up here, 73, that hydrogens are colliding one after another, and eventually 4 of them will collide to create a new atom, a helium atom, and they will release energy in the form of 2 gamma rays. And that's how the sun supports itself from gravitational collapse. That's how it maintains hydrostatic equilibrium, by this energy that leaks throughout the star. At some point, the sun is going to run out of hydrogen to fuse, because there's only so much volume in the core that is actually hot enough for fusion to take place. I don't suppose anyone remembers the temperature at which hydrogen nuclei will begin to fuse into helium, do we? That'd be the kind of thing I'd like you to know.
15 million kelvins.
15 million kelvins, that's right. And not every part of the star can be that hot. Let's go to main speaker view here for a second, and let's click on me. Okay, so I have a star. Our sun, of course, has a radius of 700,000 kilometers, which is insanely big compared to the planet Earth. Remember that day that we had to calculate the diameter of a sunspot, and it turned out to be 4 times the size of Earth? That I was hoping that would be an eye-opening experience for you guys. What part of the star can get its temperature up to 15 million Kelvin? Probably only the central 15 or 20%, right? So here's the core, and this is where hydrogen can fuse into helium. A star is not a uniform solid object like a block of wood. It has a density which varies from the outside to the inside. Not only does the temperature go up, but the pressure goes up and the density of particles go up. And we should actually expect that, right? That's how the ideal gas law works. What makes the center of the star hot anyways?
The pressure and the fusion reaction.
False.
Oh,
If
wow.
you needed fusion to make the star hot enough for fusion, you'd find yourself like a dog chasing its tail, right?
Yeah. I thought that the fusion keeps up the hotness.
The fusion does keep up the hotness, but how does it get hot initially?
By gravity squeeze.
By the gravity squeeze, that's right. Now, I happened to figure out a trick to get one of my old Flash animations working. You guys will remember that I've been struggling with this all semester. And, you know, perhaps we could just, for no other reason than I've been dying to show you this every time we talk about the ideal gas law. Oh, please say it's still working. Yeah. Can you guys see this thing?
Yeah, I can see it.
Cool.
Didn't we do this before?
I definitely would have showed this to you in your previous semester in Astronomy 1010. But people, so Mateus and Andrew have seen this little gimmick before, but it's a good gimmick, so we can check it out again. Let's pump it up. Pump, pump. Okay, so here comes some gas particles into my box. Oops. Sorry, I want to deactivate gravity for a moment. All right. You'll notice that I've got a bunch of, let's call them hydrogen atoms, okay? And they're all smashing around together. Actually, if we really wanted to make this like the sun, we could actually use two species. Let's clear this out. Let's reset. Let's add some hydrogen. So I'm going to add a light species. Here's my hydrogen. Pump. And let's add the tiniest bit of helium to it. It should be 1 helium atom for every 10. Boop, 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 boop. Okay, there we go. Here's some hydrogen and some helium gas. You'll notice that the gas particles are in thermal equilibrium. They all have the same temperature. Because the hydrogens are a little bit less massive than helium, actually 4 times less massive, they will have faster average velocities than the helium at the same temperature. Remember that temperature measures kinetic energy, not exactly velocities. And kinetic energy is 1/2 mv squared. You can see the pressure is about 1 atmosphere or so. That's roughly the pressure of air in this room, 100,000 pascals, 14.7 pounds per square inch. The temperature is around 300 Kelvin. That's pretty close to your body temperature, right? If you do 300 minus 273, my brain isn't even there today. So 27 degrees Celsius. Okay, maybe that's a little bit warmer than the air in this room, but you know, maybe not. What's room temperature in Celsius, Vladimir? Help us. Help us.
It's 18 for me.
Huh?
In my room, it's currently 18 degrees Celsius.
Wow. Okay. So that's a little bit warmer, but this is a temperature that we might find on planet Earth. You guys know what's going to happen to the temperature if I take Mr. Robot here and I squeeze the box, right? What's going to happen to the temperature?
It will increase.
Yeah. And so does the pressure. What property of the ideal gas law am I changing when Mr. Robot squeezes the box? You're muted, Mateus. If you were trying to
Pressure?
talk. The pressure is going up, but that's not the direct property of the ideal gas law that you're changing.
The space that you allow gas to occupy.
I don't remember that being one of the variables in the ideal gas law, but you're not wrong.
K, temperature K is...
K is the Boltzmann constant. It's just a number. Forget about K. K is 1.4 times 10 to the negative 23 joules per Kelvin. That's not a property that can vary. That's a property having to do with gases. So if I squeeze the box, which parameter of the ideal gas law am I changing?
N.
And what is N again, Vladimir?
I guessed that it's N, but I do not remember what.
Well, it's not pressure and it's not temperature. Those are the things that are being affected once I squeeze the box. N stands for number density. It's
Okay.
particles are in a cubic meter.
Particles per number.
When you squeeze your box, you're not changing the number of particles, but you are changing the size of the box. And a smaller box means a larger particle density, correct? That's what's changing in the ideal gas law. Changing N obviously can affect the temperature and the pressure of your gas. Watch this. Let's expand it. Notice that the pressure drops, but the temperature is still quite high. Let's add some ice. Let's cool this thing back down to like 300 Kelvin or so. And now, friends, let's try to make this thing more like a star. What's going to happen when I add some gravity? Based on what we talked about before.
When you gravity, everything's just gonna keep like floating, but it's gonna go up.
What is going to go up? What is it?
The particles that you have more of. So like
No,
all the rest.
I will have the same number of particles, Andrew, be careful here, We must be precise. When I add gravity, the number of particles will not change. What
I
will
think
change?
they're gonna concentrate on the lower part of the box, depending on
Yes.
how much gravity you add.
Yes, and I'm going to add lots. And once I concentrate at the bottom, what will happen to their state variables like pressure and temperature and number density and such?
I think it will rise.
Let's
I
find
think it will
out, shall we?
increase.
Here we go. Watch the temperature gauge when I add this gravity. Whoop. Did you see that thing shoot up? Gravity squeezes gas and it makes it hot. Well, let's make it like a real star. We actually don't even need a box, do we? Gravity is the box. Okay, there's some particles boiling away. We can call them the solar wind or something. Let's add a couple more. Pump, pump. Okay. There's something else going on here that's like a star. Let's break it, okay? Let's add a shitload of stuff. Let's really make it like a star. Okay, here we go. Now this gas is on the verge of being degenerate. I need to talk to you guys about degenerate gases today. So this is kind of fun. We're watching the particles all boil away. If I were to draw a line, like a line along the radius of a star from the outside to the inside, the density would not be uniform. It would be very tenuous at the edge of the star, and it would get much denser towards the core. Now I want to show you some big boy diagrams, okay? Let's look at some big boy diagrams together. The kind of thing that you would look at if you were, say, a senior or a graduate student. You might want to know, and you know, I'm going to attempt to bore you here. I'm going to try to challenge you to look at some boring stuff. Let's look at the density profile of the sun. And I think I'm going somewhere with this. I'm not entirely sure, but I think I'm going somewhere with this. And I want to show you guys a famous graph. Here it is. And this is to get you thinking about how the density of gas changes from the surface of the star down to its core. You have a convection zone, a radiation zone, and a core. Notice in this slightly more professional model, they actually estimate the core to be at almost 25% of the sun's radius, which is pretty wild. Now, out here, we're at the edge of the star, where the radius is, this is measured in solar radii, right? So we're at 100% of the sun's radius. Let me get my arrow tool. And we can see that the density is something like 10 to the minus 6 grams per cubic centimeter. That's pretty tenuous. The air in this room, well, let's find out. I usually know the number density, but let's write density of air at sea level. Hopefully they'll give it to me in grams per cubic centimeter. Okay, here we go. 1 kilogram per cubic meter. Are we good enough to convert that? Yes, we are. So if it's 1.2 kilograms per cubic meter, let's do some dimensional analysis. We've got to go 1,000 to 1. Oops, sorry, I'm messing this up. We have to multiply by 1,000 to get to grams, but then we have to multiply by cubic meters to cubic centimeters, 100 cubed. So 1.2 times 1,000 divided by 100 to the power of 3. Oh yeah. So at 1 times 10 to the minus 3 grams per cubic centimeter, don't ask me why that took me so long. The outer layer of the sun is how many times less dense than the air in this room that we're breathing? Talk smart to me.
1,000 times less dense.
Right. It's 1,000 times less dense than the air in this room. The edge of the sun near the photosphere is ghost-like. By the time we get to half the sun's radius, here's water. You guys know what 10 to the power of 0 is, right? It's 1. And famously, water has a density of 1 gram per cubic centimeter. They designed density to work like that, okay? Water is a good reference point. So by the time you get to roughly half the sun's radius, the density has gotten to be about that of water. Look what happens as you get in towards the core of the star. 10 to the power of 2 is 100. and it's gone over 100. Maybe it's like 200 grams per cubic centimeter. But here's where I really need you to understand some things about density. Let's look at the periodic table of elements, the Sergeant Welsh one, which is full of information. And let's look at the density of some of our favoritist elements from the periodic table. This is a nice 2000 pixel version. I'd like to point out in this legend with zinc here that the densities here in grams per cubic centimeter. Zinc is a pretty dense metal. It's 7 grams per cubic centimeter. What else can we find? What would you think would be some of the densest stuff in the periodic table? Maybe
I'll go like plumbum.
platinum or?
No, plumbum, lead,
Oh, okay.
if that's how you pronounce it.
Well, we say lead. I don't know how. Or you give me the Latin name.
Platinum is what, 21?
Here's lead. What do we have for the density of lead?
11. Wow, pathetic.
Right. Now,
Oh,
it turns
mercury.
It
I'd say
turns out
mercury.
right here, guys. Oh, sorry, Andrew, what were you going to say?
I'd say mercury's pretty dense too.
Mercury's 13 grams per cubic centimeter. The actual densest two elements in the entire periodic table of the elements are osmium and iridium. Iridium is actually a really cool, very rare Earth element, which is mostly actually found in the compositions of asteroids. One of the ways you tell if your meteorite is a rock from space or not is by testing it for iridium. There are high concentrations of iridium in asteroids, but not on Earth. These densest elements, osmium and iridium, are about 22 or 23 grams per cubic centimeter. How does that compare to the density of hydrogen and helium at the core of the sun? What's my point that I'm trying to make?
It's like 5 times less dense.
Yeah, like this material is so compressed, I'm not even sure it resembles anything from our normal world anymore, right? It's been compressed to shit, for lack of a better word. And let me say something else. That means a greater fraction of the mass of the star is concentrated at the center of the star than on the outside, right? In fact, you'd be surprised at how much mass is concentrated. Let me see if I can find the mass profile of the sun. Here, I think is this the mass profile of the sun? That looks like it's in French or something. Let me try instead of density profile. And here's where I'm going to get to my point. All right, I'm slowly but surely, in my own clumsy, meandering way, getting to a point. That's too small. I need something that shows both radius and mass. And I know this. Here we go. This figure, we have to be smart about how we read this here. And I don't know if I'm going to be that smart today. Okay, so let's see. At 1 solar radius, we contain the entire mass of the sun, right? But notice, if we go down to the core, 25% or so, what fraction of the sun's mass do I contain?
Well, half.
Holy shit, Vladimir. I have, okay, let's look back at my diagram and try to understand my point. Just in here in the core where the fusion's taking place, that's 0.5 solar masses worth of material. What if I plucked this thing out with the hand of Odin? I reached in to the star and I plucked its core out like an Indiana Jones when Mola Ram pulls that guy's heart out, okay? And I held the beating heart of a star, Indiana Jones style, up. That thing, that core of the sun, it would itself be a star. If that was a star, what would its spectral type be?
Probably like, okay.
These are the kind of questions I'd want to ask you during an exam.
Oh, beautiful and fun girl,
Kiss me.
kiss
Oh,
me.
beautiful.
So it's like K
Oh,
or
be a
M.
fine girl, kiss me. If I had, oops, sorry. If I had a 0.5 solar mass lump of hydrogen and helium, what would my spectral type be?
So K.
Yeah. The point that I'm trying to make, guys, is there's a star in my star. There's the entire core of the sun is basically like a whole nother star. It would be like the equivalent. This would be more of a star than Proxima Centauri was. Okay. Now, this is starting to get me nervous because here's what I'm thinking. The sun's been crunching hydrogen into helium for what? 5 billion years. Okay. And as we mentioned last time, helium is how many times more dense than hydrogen, roughly?
4.
4. So let's just make the dumbest, silliest, and stupidest analogy. Let's say that the sun's halfway through its life, so it's used up half the reservoir of hydrogen it has available inside the core, which doesn't have to be true, but we're just going to pretend for a second. Then today, 4.6 billion years after the sun formed, this is what the core ought to look like. Roughly half of its volume should have been inert helium. Remember how we talked about helium sinks towards the center of the star because it's more dense?
Yeah.
And hydrogen fusion should be happening here in a shell that surrounds the core, except for our sun, the shell should actually be quite thick. So really, this is not fusing, and this stuff is fusing. And each day, the little lump of helium gets bigger and bigger and bigger. I've got some awkward and uncomfortable questions to ask you. What maintains hydrostatic equilibrium in the inert helium core? Because gravity is still pressing down on that thing with half a star's worth of matter, right? But the fusion is happening in layers above it. So why doesn't gravity just crunch this into a black hole? What's going to support hydrostatic equilibrium within the inert core of a star?
I'm thinking like, just because helium is inert doesn't mean it cannot be hot. Because you said the temperature necessary for its fusion is like 100 million kelvins. But like, it's still 15 million kelvins hot, right?
Right. But the problem is energy is flowing upwards and out of the star. This is a problem. I guarantee you it's a problem. And there's an answer to the problem, but you're not going to like it. We're going to have to talk about it. This part of the star, the part that's not undergoing fusion but is still in the core, it's ultimately supported by a pressure that is not related to the ideal gas law. Let's take a note on this because I don't know how to format it any other way. And then we're going to get back to that chart, but I'm working towards explaining how a red giant forms, okay? So here's a note. The inert, and by inert here I mean non-fusing. Usually chemically inert means it's not reacting, but you know, helium is a noble gas, so I could mean it in all sorts of ways. The inert helium core of the sun or other one solar mass star is not supported by either fusion or what we would call thermal pressure. Thermal pressure is the normal ideal gas law that you saw me tinkering with inside the box. The helium core is supported by a quantum mechanical fluke of matter called degeneracy pressure. Degeneracy pressure is a new concept because you've never experienced matter behaving like this in your normal, everyday, pedestrian temperatures and pressures that you find yourself in on the surface of Earth. In a normal gas, in a gas that obeys the ideal gas law, you have a box, and in the box there are gas particles, and the space between the gas particles is many, many times the size of the gas particle itself. And they basically behave kind of like ping pong balls do in a box. They bounce around with some velocity, they smash into their neighbors, but there's a lot of space in between the gas particles. In a degenerate gas, you squeeze them much closer together than they are comfortable being. In fact, in that helium core of the sun, the helium atoms have become so closely packed that the diameter of the atoms themselves is potentially greater than the I don't know if you guys can hear me because I'm mumbling into the board. The diameter of the atoms themselves becomes greater than the interparticle separation. In other words, they're kind of like a carton of eggs stacked on top of each other. Ultimately, matter, protons, neutrons, electrons, helium nuclei, they're actually wave-like in nature. They're not entirely solid. The protons, the electrons, the neutrons, they have wave-like properties. And some of their quantum wave-like properties become manifest when you squeeze a gas to this level. If you've taken a chemistry class and you ever had to stack electrons inside of an atom, you might have heard of this weird effect in quantum mechanics called the Pauli exclusion principle. The Pauli exclusion principle, at its outset, says no two quantum particles can have exactly the same state. They can't have the same spin and angular momentum and quantum number. And that just starts to sound, well, a little wiggity wackety. So let me give you a much stupider version of the Pauli exclusion principle. It's basically saying you can't have two electrons or two protons. They can't really, it's not exactly saying this, they're waves, so they can overlap. But if they were particles, it's sort of the equivalent of saying that they can't overlap one another. At some point, they're pressed up against each other, and the two particles have to be different in some way. They can't have exactly the same energy state, angular momentum, spin. They can't, another dumb way to put it is maybe they can't occupy the same space. And so the pressure that supports the gas is no longer the particles bouncing around and colliding with each other. It's the electrons themselves, or it's actually the helium nuclei. Actually, no, I'm sorry. It's the electrons that are trying not to overlap one another and occupy the same state. In fact, there are many different flavors of degeneracy pressure. The helium core is supported by electron degeneracy pressure, meaning before the nuclei come in contact with each other, the pressure of the electrons not overlapping with each other is preventing the gas from collapsing. Electron degeneracy pressure is so potent, it can actually support the weight of half a solar mass or more worth of material. Sometimes people make an analogy of degeneracy pressure is sort of like stacking a bunch of books on a carton of eggs. If you lay one book on top of another and you do it slowly and careful, a carton of eggs could support a weight of books. There is a mass at which no matter how carefully you lay the last book on, it will collapse and crush the eggs. But you can support quite a bit of matter through degeneracy pressure. Okay, we're going to return to this later because degeneracy pressure is going to play a big role in the end of stars. But the gas inside the core of the sun, it ain't normal. Now let's try to imagine what happens on the 10 billionth year of the sun's life when it's basically used up almost all of its hydrogen. Here we'll go to a picture from the book. And this is kind of where I ended off last time. So, you know, I'm doing my thing where I take too long to explain a thing. The helium core, as you add matter to the degenerate core, it will get more gravitational pressure, but the thermal pressure will not be, the thermal pressure is kind of disconnected from the star. So every time you add fresh helium onto that core, it contracts and gets smaller. Your hydrogen fusion is now relegated to a thin, crispy shell surrounding the helium core. And every time the helium core contracts, fresh hydrogen from above can spill down into a region where it's capable of creating fusion. Although this makes no sense at all at first, fusion, the rate of fusion is so sensitive to temperature that this shell of fusion can actually temporarily produce more gamma rays than what's called core fusion. This thin little shell is contracting and contracting. The temperature goes up, and it temporarily produces so much fusion that the outer layers of the star begin to puff out. And you've got to think that that's very counterintuitive. You would think that when the star runs out of fusion, gravity should collapse it and it'll turn into a black hole, right? That's what seems logical. But instead, the star becomes like two stars at one, which we've already kind of come to terms with. There's a contracting star in the core, which contains quite a bit of mass. Then there's an outer envelope, which is expanding. This star is no longer in thermal equilibrium because it's a star that's become disconnected from itself. Let's take this as a note, and then we're going to start working on that table again. But this is something that we needed to kind of draw out and think our way through. Final note before we work on the table. A red giant is formed when a contracting, I guess we would call it helium core, develops what we would call hydrogen shell fusion. And we're going to underline that term because shell fusion is different than core fusion. This shell can produce more energy for a short period of time.
And by short, you mean like 100,000 years or something?
100 million years. Well, we're going to talk about the timescales for red giants. Red giants turn out to have several different stages, Vladimir, that I want to go through in today's lecture. But the entire we expect the sun can squeeze another 1 billion years, roughly, out of its lifespan as a red giant. But you got to let me work up to that because there's different stages of, the red giants actually have 3 different stages. We got to go through that. So, but first I just want to get you comfortable with the idea that there is a concept called shell fusion, and shell fusion is a little bit different than core fusion. And so let's put those 2 terms down so we have them at our disposal now. So I want to contrast hydrogen shell fusion with hydrogen core fusion, which is what the sun is doing today. Actually, speaking of high temperatures, the heat's on and I'm starting to get to the fusion point myself. So just let me turn the heat on. A star is a big, fat, massive object. It doesn't have to all behave in unison like a single thing. This stage, this takes a while to introduce to new students. How can a star run out of fusion and then get bigger? It doesn't make any sense at first. It's because the star is no longer in hydrostatic equilibrium. That's a key concept. Let's write that down. A red giant for a time. Actually, the very first stage of a red giant is called the subgiant phase. Is no longer in hydrostatic equilibrium. It has a contracting core and an expanding, the other layers above it, the radiation zone, the convection zone, the photosphere, we call it the outer envelope of the star. Now, you could ask me this. How do astronomers know this? The answer is twofold. It took a long time for us to figure this stuff out. One method to figure it out is by computer modeling. So theorists will actually build a model of a star, all right? They'll put something like several billion point particles that represent hydrogen atoms into a simulation. They'll calculate the forces of gravity using computers, which are good at doing many, many calculations at once. And then they will watch the star evolve and try to figure out what happens. The computer simulations are never good as real stars because a real star contains 10 to the power of 57 atoms. We do not have computers that are powerful enough to compute a model of a star with 10 to the power of 57 atoms. We will one day. It's coming. In the meantime, what they do is they try to build the biggest, bestest supercomputer they can, and they will get as many particles as they can to make it as real as possible. And I don't know what the actual numbers are, but this kind of research is done at the Los Alamos National Laboratory. Some of the same bright minds that study nuclear fusion and the physics of stars are the same people who do calculations on nuclear bombs and things like that. Some of the fudge factors and some of the calculation factors are actually regarded as state secrets, and you have to get clearance to actually work on these simulations. It's pretty wild. That's the theorist way, which of course always interests me a little less. The observational way is people figured this stuff out by studying the locations of stars on an HR diagram and then trying to think through the physics of what happens. And this is a more challenging one, but it's the one that would be interesting for us to think about. So let's go back and let's look at some real HR diagrams, because each day you guys learn more about stars and become more interesting to have a conversation with. So here we go. And I want to look at a real HR diagram. I showed this to you last class, I believe. This one was taken with the Hipparcos satellite. And the takeaway from last time was that a great majority of the stars are found along this diagonal, which you guys know as the main sequence. And for a while, astronomers could say, well, most stars have some kind of a relationship between their temperature and their luminous output. And these stars are all acting normal. But they had to wonder, what's up with these stars? These stars seem to be doing their own thing. Now, because they're diagonally up and to the right, these stars clearly have bigger radii than their contemporaries on the main sequence. The fact that there are smaller numbers means they're going through something weird and extraordinary. Let's try to imagine the journey of the sun as it transitions from a main sequence star to a red giant. Maybe I'll even take you through the 3 stages of a red giant, and then we'll get around to working on that chart. So from my other slideshow, from my evolution slideshow, I want you guys to look at this. This is the story that they eventually pieced together. The astronomers had to learn this problem backwards. They knew, based on the position of a star, what its temperature is. They know what its luminosity is. And they also know where its radius is based on its position like that, okay? As the sun turns into a red giant, it's going to begin to expand. And as the star expands, it's going to cool. Notice the surface temperature of the star is dropping from 6,000 Kelvin down to 4,000 Kelvin. And this is what makes red giants red. As their surface temperatures cool, their wean peak shifts towards the red or infrared end of the spectrum. Their radius is increasing, so they're moving in that direction on the HR diagram. But remember, we talked about this last time, the luminosity of the sun is going up. And you guys remember why that is, right? Why does the luminosity, the light output of the sun, increase? All right, let's cover this again. The sun,
Because of the radius squared factor. It
yes.
grows too much.
Okay, can you just put that into like simpler terms? You are correct.
Oh,
It is because of
so-
the radius squared factor, but what's a simpler way to say that?
So luminosity is dependent on temperature to the fourth and radius to the second.
Right.
But changes in temperature are measly compared to the changes in radius. So it
Right, the
overcomes.
radius squared factor on. And so the simple answer I was looking for, Vladimir, is there's more surface area to glow on your star, right?
Yeah.
Your star just has a bigger panels, more panels on its surface from which to glow. So watch what happens to the sun as it evolves into a red giant. In the very first stage, which we call the subgiant branch, the sun's radius just keeps growing and growing and growing. Its temperature eventually kind of flattens, maybe somewhere around 4,000 Kelvin or so. But the radius keeps getting bigger and bigger and bigger right up until this point. Astronomers found that all these different stars were evolving up the red giant branch, but there was this critical point at which they stopped and turned around. Do you guys know what's happening here at this point?
Helium is starting to fuse.
That's right. It's called the Helium Flash. In a single instant, suddenly that core hits 1 million Kelvin. Boom, the star starts to undergo helium fusion. And what do you see? Let's walk our minds through this. This is the second stage of a red giant. What do you see happening to the temperature, luminosity, and radius of the star as it goes into this helium fusing red giant stage? Let's start with the temperature. What happens to the surface temperature?
Increases by a factor of 2, maybe.
Okay, good. Maybe from 4,000 to 6,000 or more. What's happening to the radius of the star?
It decreases drastically.
All right, can you help me understand that? When helium fusion ignites, why would the radius of the star shrink? Doesn't that seem counterintuitive? Suddenly you turned on an energy bomb in the core and the radius of the star shrinks? Who can walk me through that one? Explain that
I
to
mean,
me.
you never told us how much energy helium fusion produces. Is it more intense than the shell fusion, or
That
is it
is an
less?
awesome question. Okay, so let's talk about helium fusion. Okay, this is great. This is helping me structure my lecture. That's actually something else we should take some notes on. Okay, so let's do a little section called red giants and helium fusion. And once again, just taking some notes is a good way to remember the things that we talked about. So we'll start off by saying let's say the red giant phase, because all stars have to kind of go through this. The red giant phase of a star's life proceeds in 3 stages. Okay. So stage 1 is sometimes called a subgiant. The subgiant phase is where you have hydrogen shell fusion plus an inert helium core. So far, we've already talked about this. During the subgiant phase, the radius of the star goes up. The surface temperature of the star, this is the surface temperature that we plot on the HR diagram, goes down. and the luminosity of the star goes up. That's what we talked about. At some point, helium fusion ignites. And the temperature at which the core of the star needs to achieve is 100 million Kelvin. And that's 100 million Kelvin, of course, in the core. So I'll say T core here, in case that gets a little confusing. Now we enter stage 2. Stage 2 is called a helium-fusing star or a helium-fusing red giant, except red should be in quotes because the star gets less red and gets more yellowy during the stage. Before I give you stage 3, now we'll introduce helium fusion. And this is part of today's homework too. Helium fusion proceeds by something called the triple alpha process. The triple alpha process is probably the simplest of all fusion reactions that you'll learn about today. Allow me to show you a cartoon. This cartoon is better than the books. It's just 2 measly little steps. First, 2 helium nuclei, which you will remember physicists call helium nuclei alpha particles, right? They're one of the 3 types of radiation discovered by Madame Curie. In stage 1, 2 helium nuclei whack together, producing beryllium-8 and emitting a gamma ray. Then beryllium-8, which essentially has the same fusing temperature, gets whacked with a 3rd helium nuclei to create carbon and releases another gamma ray. So let's write down the net oh, by the way, I want to talk to you guys. I want to have a kids break on beryllium in just a second, because beryllium is kind of a weird atom that's fun to talk about. But let's write down the net reaction. The net reaction is 3 heliums are basically colliding to make 1 carbon plus 2 gamma rays. So Vladimir, I'm going to turn your question back on you for a second. Vladimir asked, what's the energy yield? He actually said to me a cool question. He said, you haven't told us what the energy yield of helium fusion is. So I'm trying to figure out how well this can support the star. I'm going to trap you now, Vladimir, so be ready to be tricked. How does the energy yield of helium fusion compare to the energy yield of hydrogen fusion?
So the proton-proton chain does produce 2 gamma rays as well. However, it doesn't really have another element as a byproduct.
Yes, it does. Hydrogen turns into
Oh, of course, helium. Yeah.
So in that sense, you're trying to figure out where the trap is, aren't you?
Yeah, they're not equal, that's for sure.
They are not equal. It looks like they're equal because they both produce 2 gamma rays per reaction.
Which side to go?
The answer, look, why don't I just tell you instead of tricking you? It's about mass. It's about the reservoir of fuel that you have to work with.
Since mass is potential energy, I would say that helium fusion is more potent.
It's less potent.
All
right. Vladimir, in order to help you understand, we have to look at a famous graph from nuclear physics. Now, the book produces it, it shows it like this, but let's see if we can, it's called the energy binding diagram per nucleon of fusion. This is a legendary graph that comes right out of nuclear physics. Okay, this one's better because it actually has real units on the axis. And this is the way pros look at it. I'm going to have to walk you through this, okay? So what's being graphed? On the x-axis is the atomic number. Actually, it's the mass number, so it's the isotope, right? but they're basically telling you the number of nucleons in your nucleus. So hydrogen is over here and something like uranium is over here. So as we go up this axis, we're going up the periodic table. This tells us, as we fuse nuclei together, how much energy is released, and here's the trick, per nucleon. And a nucleon is either a proton or a neutron, correct, Vladimir? So when I go from, well, essentially here they are, deuterium. When I go from deuterium and fuse deuterium into helium, it looks like I'm releasing about 6 mega electron volts per nucleon. But to go from helium to carbon, I'm only releasing half a mega electron volt per nucleon. In other words,
There's no way I would know it.
huh? Yeah, you weren't going to know the answer to that. But I at least had to get you thinking about the problem.
Huge. Wow.
So let me make sure I explain this to everyone about. Can I erase this part up here, Andy and Mateus? Can I need a little space to work with. So in the proton-proton chain, you have 4 hydrogens producing essentially 2 gamma rays. But in the triple alpha process, and by the way, you're going to see me do this a lot. Sometimes I just abbreviate triple alpha process as 3 alpha. Okay, hopefully you guys are comfortable with this.
AAA advertisement.
Yes. So you've got one. Let me see if I can do this a little better. 1, 2, 3 alpha particles producing your 2 gamma rays. If you think about this like the gasoline in your gas tank, some gas tanks can hold 30 gallons. Some gas tanks can hold 15 gallons. To produce 2 gamma rays requires me to use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 nucleons worth of matter, right? So 12 nucleons. Okay, well, hold on a second. Class, define the term nucleon for me so I know that I'm having a conversation with people who understand me. What the fuck is a nucleon?
It's a neutron or a proton.
That's right. All of these little bits are nucleons. 4
Now
nucleons, 12
it
nucleons.
looks obvious.
So, what does this mean about the energy yield? Vladimir, let's say I've got half a solar mass of material worth of stuff to fuse. Every time I produce 2 gamma rays, I'm using 3 times as many kilograms of matter to do it, right? Obviously, you're going to crunch through that a lot faster. The 2 gamma rays are nice, but you're not going to be able to produce, you won't be able to produce helium fusion for as long. You're not going to get another 10 billion years out of this. However, you still haven't answered my question. Oh, by the way, Vladimir, and friends, I want to point out a couple of other things here. What do you guys see happening as we're going to talk about other types of fusion in a little bit? Helium can fuse to carbon, then oxygen, then sulfur. What do you see happening each time I fuse to heavy and heavier elements in terms of the energy released per nucleon?
So it's less and less.
Less and less and less. What the hell's going on with iron? At iron, it stops. And this is one of the weird things about nuclear physics. It starts rolling down the other direction.
It starts producing the energy by breaking it down.
Yeah. Iron is what's known in nuclear physics. Let's look at it. Let's look at an iron nuclei together. Typically 26 iron nuke LE. An iron nucleus is called a magic nucleus. Iron 56, the most stable of all isotopes, it has, I think, 26 protons and 30 neutrons. Notice you're having to pack more neutrons in. I was hoping somewhere I could just get a picture, a well-drawn picture of an iron nucleus. I have one in one of my slideshows, but okay. Well, I guess this is maybe as good as it gets. And that's not very good. You know, I should just use my slideshow instead. In any case, oops. Sorry, brain not working. Brain not working. I want my internet back. I want my internet back. Okay. After iron, you can no longer release energy by fusing heavier nuclei. If you start fusing helium nuclei into iron, it costs you energy and you will suck energy out of the core of the star. So on this side of iron nucleus, you release energy by nuclear fusion. On the right side of the iron nucleus, you release energy by fission. Somehow, iron nuclei are like the most perfect balance point, where I like to think of it as this is where the strong force of nature, which is gluing all those protons together, is perfectly balanced by the electromagnetic repulsion of the protons, or something like that. That's probably not a perfectly correct way of looking at it. I still want someone to answer my question for me. And now that I've gone through all this, I don't know if that helps or not. I wanted to know, friends, when helium fusion turns on in the sun, why does the radius of the star shrink? Remember that the radius is measured diagonally and up and to the right. So if my star, the sun, is taking this path, its radius is shrinking because it's moving from here to here.
So perhaps the rate of fusion and energy release is less potent, so it allows gravity to squeeze the star back
into, buzzword here, the real key is this star is returning into...
main sequence?
It
No?
doesn't quite get back to the main sequence. It will never get back there. All right, let's take notes on it. I thought
Wait, returning into what then?
Yes, returning to what? Let's take notes on it. Shoot, I just erased that stage 2. Okay, so in stage 2...
they're returning into the equilibrium.
That's it. Once core fusion turns on, the star temporarily returns to hydrostatic equilibrium. So during our helium-fusing giant star, we have a mixture of hydrogen shell fusion. So we still have a bit of hydrogen shell fusion, but now we're going to add to it helium core fusion. And during this stage, the radius of the star drops. The temperature of the surface of the star goes up a little bit. The luminosity drops. This star returns to hydrostatic equilibrium. Okay, here's the catch. It returns to hydrostatic equilibrium, sorta. Okay. I want to talk for a minute about the sorta because it's kind of interesting. There is a zone, and I need to go to my star lecture for this. There is a zone on the HR diagram. I know I have a slide on this right here. There is a zone on the HR diagram which our sun will probably pass into. It's known as the instability strip. Stars that start fusing helium but still have hydrogen core fusion, they develop this little mechanism that Stanley Arthur Eddington discovered called the helium fusion valve, where the helium nuclei in the outer envelopes become ionized and then they become neutral, and they sort of let photons sometimes leak through the star and sometimes not. Instead of the star actually being in hydrostatic equilibrium, these stars become variable stars, and they pulsate like an accordion while they're undergoing their helium fusion. So during this special stage of a star's life, you develop, let's look at a variable star GIF. Polaris is an example of one of these stars, and this is what it would look like. Where's the damn GIF? I've got it. Oh yeah. Come on, baby. This is what the star does. They pulsate. They build up pressure and they grow and they shrink. And if you were on a planet surrounding one of these stars, you would literally see your own sun growing and shrinking in the sky. Typical period pulses for these things are roughly 1 month.
Professor Britton's.
Yeah.
Yeah, you froze a little bit.
Oh.
Yeah, it's like periodically, variably, you throw.
Am I becoming a variable star myself?
A variable professor.
So I've got a little fun challenge for you to work on for the rest of your life, okay? And this is just to remember variable stars by. Polaris, the North Star, is a legendary variable star. It has a pulsation period of roughly 30 days or a month. Now, I want to find a picture of Polaris so you remember what it's like. Remember that Polaris is a helium-fusing red giant star. It's the tail of the Little Dipper. Here it is, the North Star. And you guys can find Polaris once again by using the pointer stars in the Big Dipper. Find the basin of the Big Dipper, which should be easy to see. Make a line with the pointer stars, and it points towards Polaris. The rest of the stars in the Little Dipper will be difficult. Sorry. I'm having some difficulty with my lifestyle right now. Here we go. All right. These stars will be quite difficult to see from Rhode Island, but I can see Polaris and I can see these stars pretty decently. Polaris, because it's a variable star, it varies between a magnitude 2 star at certain times of the month and a magnitude 3 star. Because of our light, remember that a magnitude 2 star is a second rank brightness star. So it's about the brightness of the stars in the belt of Orion. But a magnitude 3 star is actually kind of hard to see from our horribly light polluted skies. So I would notice the variability of Polaris because as I would teach my classes live in person, I kept taking my night courses out to the telescope so that they could actually look at some stars. And of course, I'd always want to show them the North Star because we talked about that during our stellar coordinates. But sometimes I'd have my laser pointer and I'd be like, look, it's right there. And everyone was squinting and they couldn't see it. But then I'd go out like 2 weeks later with a different group and Polaris would be bright and shining right in the sky. So I could actually track over the course of the month, seeing it go from a very easy star to see with my naked eye to a star that was kind of lost in the wash in the light pollution. You are going to be noticing Polaris over the course of your life after taking this course. Keep track of that. See if you can notice its pulsation period itself. It turns out that variable stars are insanely useful to astronomers because they turn out to be what's called a standard candle. You can actually relate their period of pulsation to their luminosity, and you can use them as beacons or indicators of the distances to objects. I'm going to have to take some time to work you through that, but next week's lab, we're going to retrace the work of Henrietta Swan-Leavitt. She was the first person who studied pulsating variable stars and figured out how to use them as distance indicators to other galaxies. In fact, I want to show you guys something. I know that this was one of those lectures where I used a pre-recorded lecture for some reason. But at some point, if you did watch the pre-recorded lectures, I would have told you the story of Pickering and the Harvard computers, those ladies that he'd hired to help do his spectroscopy measurements. I have a picture, and I probably showed this to you guys before, of the Harvard computers. Oh, come on. Where is this damn thing? Which slideshow is this? Where is Pickering's harem here? Okay, here they are. This is a slide that I found, a famous photograph of the Harvard computers, Pickering's harem, at the Harvard College Observatory. And they're obviously hamming it up and they're posing for the photograph. So they're doing all the various tasks that astronomers do. For instance, this lady over here is looking through a spectroscope, and she's probably measuring the emission lines of hydrogen or helium. These ladies are taking the spectra photographs of stars, and they're analyzing them for absorption lines. Do you guys see this over here? This is December 1889. They're tracking the star Beta Auriga, which is known as Chiliac, and they're measuring its magnitude, its pulsation period. These were some of the first people to discover variable stars. And here they are tracking its magnitude. And these were the people who actually had to figure out what the physics was. They didn't know anything except, whoa, this star is blinking. What could be causing that? Very, very cool stuff. Okay. Let's take one last look and then, well, how am I doing on time? I'm not doing great on time, but I think you guys are learning, so that's okay. Let's try to have a think about what's going to happen as the sun now begins to fuse helium into carbon. And for this, I'd like to call on another slide from my stellar evolution show. It's this slide here. This is showing you the multiple stages through which a star like our sun will go through. Let's get this out of the way and let's get you guys off to the corner. Okay, in stage one, which we call the subgiant branch, the radius of the star grows into a red giant. You've got your inert helium, but your hydrogen is fusing in the shell. The star grows. Then we went into stage two, which is here. That's where you actually have hydrogen shell fusion, but now we have another layer of fusion of helium core fusion, and that's where the star returns to hydrostatic equilibrium, except it gets kind of messed up and the star pulsates for a while. However, if you follow through the logic of what we've done so far, as helium fuses into carbon, carbon is what? 12 times as massive as hydrogen? It's going to sink right to the heart of that star, but carbon cannot begin fusion until it reaches the temperature of 600 million Kelvin. So the center of our sun will not be hot enough to fuse carbon, in fact, ever. So the carbon ash, the degenerate carbon ash, is going to start to build up inside the core until eventually not only is the hydrogen relegated to shell fusion, but now there will be a second layer of shell fusion due to helium. This is the third stage of a red giant. We call it a double shell burning red giant. Once again, the star loses hydrostatic equilibrium. The core of carbon starts to collapse and collapse and collapse. The outer envelope of the star starts to expand. In theory, if our sun had enough mass, maybe there could come a point where it would ignite the carbon fusion, but it will never get there. A one solar mass star just does not have enough gravity to crunch that carbon down to a high enough temperature to fuse it. So what happens is the star keeps expanding and expanding. After a while, the star is going to look like my pal Ada Carina. This. It keeps expanding and expanding. The outer envelope just gets pushed off. Suddenly, it just becomes disconnected from the entire gravity of the star, and it puffs out. The carbon nugget is left behind. The outer layers expand, and it becomes this, the ring nebula. This is what our sun will eventually become, the white dwarf buried in the center. That's actually a background star. I'm lying to you, but that's okay. Okay, anyway, so it doesn't matter. Pretend it's the white dwarf. Okay, you can't release the white dwarf. It's too tiny. All right, so anyways, pretend that's the white dwarf. The outer envelope, do you see this? This was once the convection zone and the radiation zone of a one solar mass star. And just like a smoke ring, it just poof, it just puffs itself to death. All right? These, for some reason, lost to time, have the unfortunate name of Planetary Nebula. Relation to planets, 0%, okay? Nothing to do with planets, but they're called Planetary Nebula because people were observing them long before they understood what the hell they were looking at. Planetary nebulae are some of the most beautiful things to look at in all of astronomy. This is a personal favorite. It's called the Ring Nebula. I show people this with my telescope all the time. Let's just look at a couple other famous ones. Here's the Cat's Eye Nebula. These are all one solar mass stars that kind of puffed themselves to death. The Eskimo Nebula, the Ant Nebula. What's going on here, Vladimir? Why does this thing look like an hourglass? Take a guess. What's
It
going
was a
on?
binary star.
It's not a,
No.
that's a good guess because roughly half the stars are binaries, but you do not need a binary to make this shape. What could be
Huh.
going on here? What would force the gas and the plasma to move?
Oh, it contracts back in at some point? No?
What might?
Mm.
This shape kind of reminds me of something. What did this shape remind you of?
I don't know. I mean, you said hourglass or ant.
Boy, this picture means nothing.
Oh, Jesus. Are you serious?
What?
Because of the magnetic field?
There must be some
No?
kind of really yeah. So can I tell you, me and the other graduate students, when the professors would ask us pesky questions like that to freak us out and to trick us up, we always had a joke among all of us is if they ask you a question about stellar astrophysics or galaxy physics and you don't know the answer, just say magnetic fields. And like 50% of the time you'd be right. Just because anytime something funky is going on in a picture and you don't know what's happening, you're just like, because of the magnetic fields. And then half the time you'd be correct, okay? So in fact, you know what this reminds me of? You can actually see the dipole structure, like just think about Earth's geomagnetic field. It's a dipole, right? So the geomagnetic, a dipole magnetic field, the Earth's magnetic field actually has that exact same structure. It looks like this, right? So all I can think of what's happening is some stars have more intense magnetic field activity than others. This thing, as it was expanding into a shell, probably had this wicked powerful magnetic field. You remember how plasma kind of gets stuck to magnetic fields? It's probably started to blast things out along the field lines, and the field lines are interacting with the plasma in such a way as to force its direction. The only other thing that I could think that's happening here is rotation. And remember, we're seeing a two-dimensional slice of this. This could actually be kind of like a three-dimensional donut of plasma, and we're just kind of looking through a slice of it. Let me show you a few of the other planetary nebula so you can just see how wild they are. The Twin Jet Nebula definitely has some magnetic field fuckery going on there. This is the Cat's Eye Nebula, or the Hourglass Nebula. The Southern Owl Nebula is really beautiful, nice spherical shell. Look at this one. This one's epic. This is like the Eye of Sauron. It's like the Helix Nebula. Now, I want to tell you that this is the white dwarf, the little leftover carbon nugget in the center. The reality is white dwarfs are very small in radius and therefore very low luminosity. Chances are that's just a background star that we happen to catch along the line of sight. But if you want to pretend it's the white dwarf, go ahead and do that because it might make you feel good, okay? I've even tried to image some of these nebulae myself. This one I did with a bunch of students 2 years ago. It's the Dumbbell Nebula, and we did this right from the Jacobi 16-inch. We composited about 30 pictures. Now, okay, so we're not the Hubble Space Telescope, but compare this to a much better version. So this is our version of the Dumbbell Nebula, and here is the Dumbbell Nebula. You can see, and we could have gotten a better image if we just took more photographs and stacked them. But here's what's a good professional version that's not too professional. This is what M27 the Dumbbell Nebula looks like. And you can see we basically got that structure. It's got some hot red gas in this kind of sickle shaped, right? And you can see that we got that same thing there. Isn't that rad? I was very proud of us. I'd like to do more of this with students. That's a project I have going forward. Okay, Before we end our lecture, let's finish the notes, okay? Stage 3. In stage 3 of our red giant, we call it a double shell fusing red giant. This is the third stage that our sun will eventually go through. What's happening here is we have an inert carbon core. We have helium shell fusion stacked on top of hydrogen shell fusion. Make a note to self, this star is not in hydrostatic equilibrium. Not in hydrostatic equilibrium. In other words, the outer radius of the star goes up and it basically never stops growing. The temperature of the star, let's look at the HR diagram. Because I think there's some nuance here, isn't there? Function F584. What's happening to the temperature? I guess it's kind of dropping a little bit. Not too much though, right? Okay, well, I guess the sun went from here to here. That was a pretty decent drop in temperature, right? From here to here, it's not quite as big of a drop. I'm almost tempted to say the temperature stays flat. On this, the temperature is a slight drop. Let's just write that. The luminosity of the star is weird. It's definitely going up, but at some point when the star distends and it becomes disconnected, and when it turns into that cool planetary nebula, eventually the luminosity is going to go way down. So the end state, and we'll be working on this next week, is a carbon. The nugget that's left behind that we're going to have to talk about because it's wild is a carbon white dwarf. That was the core, plus a planetary nebula. And one day that will be the fate of our own sun. Okay, what didn't I do today? I was eventually trying to get back to that graph. Remember the table with all the stages? That's okay. Because if I had just put things into these boxes, there wouldn't have been a good picture. Today we worked on the pretty picture. Next class, I'll fill out the table and we'll talk about high mass stars. High mass stars are going to have a whole different thing going on. And our homework today will involve a little tiny bit of that, but let me give you a sneak peek of where we're going. How do low mass stars differ from high mass stars? I think I've got one picture that'll just sum the whole thing up. If instead of being one solar mass, our sun had been like 30 solar masses and been a spectral type B star, it would be hot enough to fuse carbon, and it would fuse other elements beyond them. Eventually, the cores of high mass stars can fuse hydrogen to helium to carbon to oxygen to neon to magnesium to silicon, but they can't go past iron. And you remember why, right? Why can't I go past iron as an element in the periodic table for nuclear fusion?
You can't gain energy by fusing iron into something else.
That's right. And once stars fill their cores up with iron, the high mass stars actually will collapse, and they will undergo a dramatic explosion called a type 2 supernova. Ain't got time to tell you all about that today, but let me tell you, it's going to be awesome. All right. And it'll be fun to talk about them are supernovae.
Wait, so I have two questions. First is so why does the red giant collapse again? Well, not collapse, but contract when it starts to fuse helium. Is it so? I said that is it because of the like lower rate of fusion that allows to get back to the hydrostatic equilibrium? But is it the actual answer?
Here's how I think about it. Before, when the star is expanding, the outer layers of the star are growing, right? But if you look at what's happening to the core is shrinking and shrinking and shrinking. Let's imagine that the core leaves a little empty gap. Fresh hydrogen spills onto it, makes more. It's kind of like the last splutters of a car when it runs out of gas. During the helium fusion stage, the star can reconnect with itself. As soon as helium fusion turns on, the core starts to puff out a bit, and the overlayers of the star can kind of sit back down on top of it, and the whole star becomes this connected thing that's balanced between pressure and gravity. So it's not easy to explain this. And by the way, the people who first figured this out, they didn't predict this either. They looked at simulations and computer models and were like, holy cow, something totally different than I expected is happening, but it matches the results that we can see on the HR diagram, right? They were like, yes, this makes sense. The star should be shrinking. So the star shrinks because the pressure is now supported by the core. In other words, it looks like the star is expanding here, but it's because the core is shrinking and shrinking and shrinking, and it's changing the fusion temperature at the shell of the star. Maybe you're not satisfied with that answer, Vladimir, and I can appreciate that. But sometimes you got to just sit and meditate on things for a while for them to feel good. Okay. All right.
Oh, and second question.
Yeah.
How hot can it get? Because like
Well,
there seems to be an absolute zero where there is no energy, but like you said, 100 million kelvins, then 600 million kelvins. Is there any boundary?
Yes. The sun cannot get to 600 million Kelvin. It just does not.
But like it's not a universal boundary, it's just a boundary for the sun. But if other stars start to fuse like carbon, that means they can reach that temperature. I'm saying like, is there a universal?
That's it.
Is there a universal boundary for hotness?
Remember the cutoff for high mass stars? At 8 solar masses, that will get you to 600 million Kelvin for helium for carbon fusion. So at 8 solar masses, this is what makes a high mass star. Then you can do carbon fusion. You'll understand more when I contrast the high. Today, I just focused on the low mass stars because I had limited time. Next time, we'll work on the high mass stars too. Okay.
But like,
Vladimir, before we piss everybody off here, although I like these questions, they're good. Why don't we take a little break so I can chug some iced tea? It's 1:40. At 1:55, we'll tackle the homework today. The good news about today's homework is it's not quite as epic as some of the other ones. The questions are really fun, but they don't take a long time to do. So today's homework will not be too horrible.
I won't return. I'll have to go to a meeting. Actually, the meeting will not be too long. It's like a high school honors thing meeting. I don't think it'll take too long, but
that's
if
okay.
I can,
you can blink in and out anytime you'd like. Just make sure you go back and nip those other questions when I post the video, okay?
All right.
All right, so 15 minutes or so to chill, and then we'll start on the homework. You guys, at least Mateus and Tegan, you'll hang out with me, right? So I'm not just talking to nobody. All right, I don't want to have to give anyone the pre-recorded video because then I would just have to take a long break, okay? That would be horrible. So please, someone stick around to talk to me for the homework. Okay, I'll see you guys in a little bit. Welcome back, everyone. It's time to do homework number 10, chapter 17. Mateus, I'm glad to have you with me. Sure hope somebody else is going to be with me. It's just you and me and a couple of trolls here. So, how do I feel about that? I guess we'll just start doing it and hope that someone else joins us, okay?
Was the computer that you were talking about earlier in class the quantum computer that they're building for a while now, I think?
No, but those quantum computing devices will certainly exponentially increase the computation power of computers, and in theory will allow us to perform more robust simulations for everything from stellar dynamics to the interiors of planets to even the way the entire galaxy or universe works. So those quantum computers are amazing because instead of little silicon switches, they're basically using the spin transitions of electrons, spin up and down, as the ones and zeros. And since you can just pack so many atoms into a tiny space, the computation power will be insane. So I can't even imagine what's going to happen. You're going to have cyborgs and robots, not just doing your dishes, but maybe even telling you what, maybe we'll be doing the dishes for the robots because they're going to be smarter than us. You know, it's
Wow, that's true.
Let's get our name on the page. Let's get astronomy 1020 on the page. Let's get homework number 10. Mateus, have you got the numbers handy?
Oh, I can pull it up in 2 seconds.
Mateus, I'm tempted to just give you guys the pre-recorded version of this, but we've already come
That's
so far, and
cool.
maybe let's do a couple together anyways and see how we feel. If
All
no
right.
one joins us, maybe I'll stick the recording on you, but I think it'll actually be better for students later too to have it one continuous recording. Let's get our numbers up here. Do you have them?
I'm pulling it up right now. Okay, so it's homework, and you said it was number 10, right?
Yes.
Yes, so it's going to be chapter 17, number 43, 49, 50, 51, and 54.
For some reason, I remember this homework as not having too many really hard crunchers. It was just easy and fun. So why don't you read me chapter 17, 43.
All right, so 43, rare elements. Lithium, beryllium, and boron are elements with atomic numbers 3, 4, and 5 respectively. Despite there being 3 of the 5 simplest elements, figure 17.15 shows that they are rare compared to many heavier elements. Suggests a reason for their rarity. Hint,
Okay.
consider the process by which helium fuses into carbon.
Okay. This question is about a famous graph known as the cosmic abundance. Ooh, I would have liked to have that periodic table of the elements up here. Let's get that back. Sergeant Welsh periodic table. And this was the one. And let's also, while we're at it, look up another famous graph. This one is, I've got a slideshow for it. It's called the cosmic abundance of the elements. This tells us how rare or common elements in the periodic table are. And it actually stands for elements anywhere in the universe, from our planet to mostly interstellar nebulae. I was trying to find a nice big picture of this. This is slightly better than the one that I have in my slideshow. Okay. So obviously, if the majority of the interstellar medium, where stars come from, has roughly the same composition as the sun, hydrogen and helium are clearly the most abundant elements in nature. And this graph is actually a logarithmic graph. So you're not just plotting numbers of elements, you're plotting 10 to the power of some power elements. So for instance, 10 to the power of 0 is 1. So they've scaled the whole thing to one of the least abundant elements in nature, which is beryllium. And relative to a beryllium atom, you get 10 to the power of 10 hydrogen atoms, 10 billion. So You have to count through, in outer space, you have to count through 10 billion hydrogens just to find one beryllium atom. That's how rare beryllium is. But notice the trend here. As we go higher up the periodic table of the elements, the abundance of the elements drops because it's more difficult to fuse heavier and heavier elements. In fact, our sun can fuse hydrogen into helium, and one day we'll fuse helium into carbon, and then it stops. I didn't quite get to high mass stars today, but high mass stars will be able to continue to fuse carbon to some of these other elements, but even high mass stars have to stop here. There are, of course, many elements on the periodic table after iron. For instance, let's just take some common ones. Nickel, copper, zinc. Gold and silver come after iron. If you were to ask me, how do these other elements get created if they can't be done in fusion? The simple answer is these elements are produced at the very end of a high mass star's life. When it actually goes supernova, it undergoes microscopic bursts of fusion during the explosion. So all of these other elements, they all come from the dramatic supernova explosion that high mass stars will go through. So they're not even really created during the star's main life. They're just created at the very end in the last explosion. And you can notice a big drop in the abundance of iron as we go to elements beyond there, because such small smatterings of things like lead and gold and protactinium are created. And yet there's something weird going on. The third, fourth, and fifth simplest elements have a berserkly low cosmic abundance relative to all the other atoms. Naively, one would think that fusion would go like this. Hydrogen fuses to helium. Helium fuses to lithium. Lithium fuses to beryllium. Beryllium fuses to boron. But it actually doesn't work like that. Fusion has its own logic, a logic we have to learn. Now, Mateus, they suggest that we consider the process by which helium with 2 protons fuses into carbon with 6 protons. And you learned about that nuclear reaction today. Check out your notes and tell me what's it called.
Helium fusion?
Yeah, the name of that reaction. Helium fusion, just like hydrogen fusion goes by the proton-proton chain or the CNO cycle. What's the name of the reaction?
It's not double shell fusing.
Nope, that's a stage of a red giant's development. We need the name of the fusion reaction. You must have written it down because you were writing down everything I did, right?
I was, yes.
This is where it would help to have a few more people participating. Brian, Zach, Marshall.
Hydrogen core fusion?
No, that's a stage in a star's development. This is the nuclear fusion reaction itself. It's buried in there somewhere. Let's see if I can pick it out of my notes. Here's a big hint, Mateus. Psst, it's on my screen. It's like right there.
Triple alpha process?
Oh, right, the triple alpha process. Of course, that's what it's called. Okay, so this question is about the triple alpha process. So helium to carbon fusion, it proceeds by a reaction known as the triple alpha process. Let's write it down again, Mateus, until we memorize it. All right? 2 steps to the triple alpha process. In step 1, a helium nuclei collides with another helium nuclei. It creates beryllium-8 and a gamma ray. In step 2, our newly formed beryllium-8 gets smashed by another helium nucleus, and it forms carbon-12. plus a gamma ray. Matthias, do you see any connection between this reaction and the reasons why lithium, beryllium, and boron might have such a rare abundance in nature? It might also help for you to know that we know a lot about the Big Bang by studying the leftover radiation from the Big Bang. It's called the cosmic microwave background. And we know this with certainty, Matthias, that after the Big Bang, the entire universe only consisted of two elements, hydrogen and helium. And there was virtually no other atoms in the universe. So all this other crap that we find out there when we dig holes in the ground and sift through atoms, there's only one place that other stuff could have come from, and that's the interiors of stars. Why would lithium, beryllium, and boron have such a low abundance relative to the other elements of the periodic table?
Because maybe this is just, I'm just inferring, maybe all the material, I'm sorry, I just lost it. Like maybe there isn't enough of it because there aren't as many stars exploding right now.
No, it's about this. It's about the way. So maybe what we need to do is we need to draw out a couple of helium nuclei. All right. So let's draw two helium nuclei. We got two protons shown in red.
Mm-hmm.
We got two neutrons shown in black. And now we're going to draw another helium nucleus. If I smush those two things together, what am I going to get? I'm going to get
two of those things? Oops.
Yeah. So if I smush helium, if I smush these two atoms, these two nuclei together, what will result? A new nucleus.
Yes.
And what will that new nucleus have?
Is it the beryllium plus gamma ray over there, or?
Well, the gamma ray is the energy. It's the beryllium 8. So
okay.
What should beryllium 8 look like? Help me draw this nucleus.
Oh, so there's going to be 4 protons and 4 neutrons?
That's right. So 1, 2, 3, 4. And then we got to add some neutron glue in there. 1, 2, 3, 4.
Right.
Okay, but what would the nucleus lithium 3 look like?
I'm not following.
Lithium has an atomic number of 3.
Okay.
And that tells us the number of protons in the nucleus, right?
Yes.
So probably it has
3 protons and 3 neutrons?
Most likely, yeah. In a way, Matthias, this.
Oh, okay. Mm-hmm.
Now you starting to follow me?
Yeah.
Why would this be such a rare element when these are so common and carbon is so common? Let's just forget about beryllium for a second. I mean, last time I checked, 2 plus 2 equals 4, right?
Yeah.
It's hard to imagine how you could make 3 when you have only 2s to work with.
Right.
So what's my point? Why might these elements be rare?
Because the elements that are in abundance like exceed 3, like they don't really, like lithium isn't the direct product of the chemistry of these elements.
These elements get skipped in fusion. For some reason, in nature's choice, it's not our choice, nature doesn't want to fuse helium into lithium. In fact, it couldn't, because all it's got to work with is a complete core of degenerate helium, and you can only smush together heliums. The best you could do is create beryllium, but the problem is beryllium fuses at the same temperature. These elements are getting skipped over in the fusion process. And
so
as
how are they even made?
Once again, supernovae. In fact, probably not even in supernovae, but sometimes in outer space, there are floating around elements of iron and stuff, and they'll get hit by a cosmic ray. They call this spallation. Basically, a high-speed proton shoots out of a quasar in some distant galaxy, travels all the fuck through the universe, randomly smashes into a big fat iron nucleus, breaks it in half in some goofy way, and a microscopic smattering of lithium comes out. Thank God you're here, because Vladimir, because I'm putting so much pressure on poor Mateus. I was actually thinking about turning this over to my robot version of me, but
Where's everybody?
it's okay. All I need is you guys in my life. That's all I need. All right. All right. Listen.
Kind of happy, to be honest.
So hold on. So let's have Vladimir, since Vladimir's just joined the convo, and you really haven't missed anything, Vladimir, because I'm doing exactly what I said I wouldn't do, and I'm taking a lot of time here. I want to show this graph in a different way. This graph, the famous graph, is known as the cosmic abundance of the elements. And let's make sure that you guys have the machinery 105 to read this. Oops, here we go. Okay, this graph was done in a weird way because they basically scaled it all to a hydrogen atom. So they have a hydrogen as having an abundance of 1, and they're showing the other elements as a percentage of hydrogen. For instance, you will notice, according to this little picture here, that if a hydrogen is at 1, the relative abundance of helium is about 10 to the minus 1. Okay, so how many hydrogen atoms do I have to count through in space to find 1 helium?
Kind of like 10.
10, because helium is 1/10 the abundance of hydrogen, right? Because it's 10 to the minus 1 is 1 over 10, 1/10. Okay, the next most abundant elements are carbon and oxygen. They have a relative abundance in outer space of 10 to the minus 3. How many hydrogens do I have to count through to find 1 carbon atom?
Ten to the 3?
That's right. And how do I say 10 to the 3 in plain English? What is 10 to the power of 3?
1,000.
That's right. I have to count through 1,000 hydrogen atoms in space to find 1 carbon. What about iron, which comes from the collapse of massive supernovae? 10 to the minus 5 relative abundance. How many hydrogen atoms do I have to count through to find an iron?
100,000.
100,000. Now, as the elements get heavier and more complex, their abundance is dropping and dropping. The only exception to this, and it's a fucked up exception, the 3 simplest elements in nature after hydrogen and helium, lithium, beryllium, and boron,
Yeah, what's
have
up?
a berserkly low abundance. How many hydrogen atoms must I count through to find a lithium atom or a beryllium or a boron?
What is this, like 10 billion?
10 billion. The book suggests, Vladimir, that this has something to do with helium fusion, the triple alpha process. What would
It avoids those two, it goes to right to other elements.
it skips over them, right? In fact, the heliums immediately form into beryllium, and the beryllium immediately gets whacked by another helium to form carbon. So nature is bypassing the odd elements because heliums keep adding 2 protons at a time. You might expect there to be some beryllium, but beryllium is kind of a fucked up element. Beryllium-8 is actually unstable. For some reason, 2 protons and 2 neutrons are really, really stable, and nature loves alpha particles, but 4 protons and 4 neutrons are unstable. In fact, the only beryllium that we can even find on Earth is an isotope known as beryllium-9. And beryllium-9 is actually kind of an interesting material. It's this gray, kind of brittle metallic element, and you can actually dope metals with them. Like the Air Force will dope the sides of jets and make super strong steel that's resistant to bullets and stuff. But this stuff is quite rare and obviously quite expensive because you really got to dig around to find this stuff. It has all kinds of interesting properties. Really, 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 really strong metal.
Is it better than titanium?
I read this a long time ago. I don't know its ranking. I know that if you typically dope other metals with it to make super strong metals. But I just think it's weird from a nuclear physics point of view that for some reason 4 protons and 4 neutrons are not stable, but 4 protons and 5 neutrons are stable. Nuclear physics is just weird. This is just berserk. Anyways, let's answer this question so we can move on. It's not a very complicated answer. So our answer is going to go a little something like this. Lithium, beryllium, and boron have, and we're going to use some fancy terms here so we remember the phrases, have unusually low, and here's the term that we want to, here's our fancy $10 vocab word, unusually low cosmic abundances. That famous graph that I showed you was known as the cosmic abundance of the elements. They have unusually low cosmic abundances in nature because these elements are skipped over in the triple alpha process when helium fuses into carbon. Let's just add another sentence or two to really flush out the answer. Helium fusion must add 2 protons at a time. So odd numbered nuclei, such as lithium, we'll put the atomic numbers in parentheses, 3, and boron, 5, are automatically skipped over. I'll just say automatically skipped during fusion. Now we'll deal with the beryllium problem. Beryllium is formed temporarily, but immediately, oh shit, spelling's bad. Immediately fuses with helium to form carbon. In parentheses, we can add for completeness that beryllium-8 is also unstable. So even if it did somehow escape the core of the star before getting whacked with another helium nucleus, beryllium-8 would self-disintegrate back into 2 alpha particles. Okay, maybe not my finest worded problem ever, but I think it gets the point across. The 2 new concepts that you guys were exposed to today is the idea of the cosmic abundance of the elements and the triple alpha process. And by the way, you know, people, they fight global wars over in economic wars and physical wars. These cell phones are powered by lithium-ion batteries. Lithium has a low abundance on Earth, just like it does on space. And for that reason, the control of the global lithium market controls who makes and produces cell phones. And these issues are only going to become more important in the future as we depend on them more and more. So in a weird way, what happens inside the cores of red giant stars is related to the price of an iPhone. It's totally insane if you've got a big enough lens to understand it. Okay, are you guys done with this? I want to erase and move on.
Just a little bit more.
Okay.
With helium to form carbon. Okay. Okay.
That's just more time for me to sip my Arnold Palmer right here.
So there's alpha, beta, and gamma decay, right?
You mean alpha, beta, gamma particles in radiation?
Yeah. So alpha is helium. Beta is, what is beta?
A free electron.
And gamma is, well, like a gamma ray.
Yeah, so actually, perversely, the third particle radiation is more of an electromagnetic wave than a particle. Except it's fucked up because when the wavelengths of photons get really short, they actually behave more particle-like than they do.
Wave-like.
Right. And did I show you guys the Geiger counter and my lump of uranium and stuff?
What is it?
Oh, that's a secret, dangerous surprise. Remind me that there's a dangerous demo that I would like to perform next Tuesday, okay? Remind me about the dangerous demo.
Okay.
All right. Can I erase now?
Yeah.
All right, let's try not to take as long a time on the next problem. So that's chapter 17, number 49. Vladimir, or actually, do you have, Mateus, do you have the questions handy? Whoever's got them, read them to me.
Yes, I have them.
All right.
All right, so 49. Escape velocity from a red giant. What is the escape velocity from a red giant with a mass of 1 sun mass and a radius of 100 sun radius? How does that velocity compare with the escape velocity from the sun? Describe how your results help account for the fact that red giants have strong stellar winds.
Okay. So this is just a silly little problem to help you think about red giants and their gravitational pull in comparison to a regular old star like our sun. So this is the mass and radius of a red giant. One day our sun will become a red giant, and its mass will stay the same, but its radius will swell to a factor of 100 times its current radius.
So
Vladimir?
it's easier to escape.
That's right. Why is it easier to escape a red giant?
Because the escape velocity is the square root of 2gm over r. So if r increases, then the escape velocity decreases.
That's the whole point of this. And I'm glad you can see that. Okay, so we did this problem once before. Let's give you the Blitzkrieg version. And by the way, I just want to check something. Did I have any problems crossed out there? This problem is really stupidly easy. Vladimir, let's give you the numbers right away. Let's first do it for the sun, okay? One solar mass is 2 times 10 to the 30 kilograms. And the radius of the sun, I'll just give it to you in meters because I don't care right now, is 7 times 10 to the 8 meters. So let's go ahead and let's find the escape velocity of the sun. I'll make you do one computation, 2 times 7 times 10 to the minus 11 meters cubed per kilogram per second squared times the mass 2 times 10 to the 30 kilograms, all divided by 7 times 10 to the 8 meters. Punch them up. My marker's dying here. I like it now. Get it all. Give me a freshie. Oh yeah, it's a freshie. All right, what you got?
something like 600,000 meters per second. Very
No,
roughly.
you forgot
No?
the square root. Do I have to do this?
No, wait. Times 2. Okay. Times 2. 2 times 7 exponent negative
Y'all be
11.
slow. 2 times 7 exp minus 11 times 2 exp 30 divided by 7 exp 8 equals square root thereof. Oh,
But
sorry.
I got this. Okay.
You were correct, Vladimir. So to 1 sig fig, what's my answer? Sorry,
So
buddy.
600,000 meters per second.
What would that be in kilometers per second?
Like 600 kilometers per second.
Good. Okay. Now, Vladimir, let's have you go off on your bullshit like you were doing before about the red giants, okay? The red giant has the same mass, but the radius is different by a factor of 100, right? Wait, so
Yeah.
everyone circle this. This is for the sun. I'm going to have to erase here, and we're going to play some slick Rick tricks because Vladimir is good enough to see those slick Rick tricks. He knows how to use a proportionality argument. To do this fast for a red giant, we will recognize that the escape velocity is basically the same thing. We have one solar mass, but we have 100 solar radii. So by what factor will the escape velocity differ? Since you're so good at math, buddy.
By a factor of 2 to the second. Square root of 2 to the second.
Aha. See, this is the escape velocity that we just calculated. And you'll notice, Mateus, what I've done is using my superior mathematical trickery, I've yanked out the 1 over radical 100 from the square root. Why would I do such a thing? Because I already know the answer to this problem from before. This problem has an answer of, all right, I need to give a little more real estate.
Real estate.
The escape velocity of my red giant then is basically just going to be 600 kilometers per second. That's this part divided by radical 100. What's radical 100?
1/10. Oh, well, just 10. Just
So what's
10.
my answer then?
60 kilometers per second. Wow.
It's 10 times easier to escape the velocity of a red giant than it is a main sequence star. Vladimir, how might that be related to the formation of planetary nebulae? And what's that got to do with that dope picture of the ring nebula that I showed you earlier?
So when it expands, it's kind of like shooting rockets in all directions.
As the star expands, it becomes easier and easier to just give up the ghost and let go of the gravity, right? Red giants, towards the end of their lives, just push plasma off their surfaces. And this is related to a really interesting observation that happened to us last year. Last year, I saw something that I had never seen in my entire lifetime. Normally, stars evolve over billions of years. So once one of those buggers is up there twinkling in the sky, your life is a mayfly in comparison, and you really don't get to watch stars evolve or change. For hundreds, for thousands of years, humans have observed the constellation of Orion, and they've had a favorite star. The bright red star Betelgeuse is the upper left-hand shoulder of Orion. It's also known as Alpha Orionis because Betelgeuse has historically been the brightest star in Orion. 1 year ago, sometime around December or so, Betelgeuse started to drop in luminosity in real time. Like I would go out at night and I would look up at Betelgeuse and it was so effed up that it was actually dimmer than the 3 stars in the belt. I think it dropped from a magnitude 0 star all the way down to a magnitude 3. I mean, you'd look up there and Betelgeuse just looked freaking weird. Now, I got excited because I thought this meant the star was undergoing a radius collapse, which would lead to a luminosity drop. And I thought we were about to witness Betelgeuse go supernova. If Betelgeuse goes supernova, its magnitude will rival that of the full moon, and you will see that star on the sky during the daytime for at least 1 to 2 months. That would be fucking wild. Oh, and then it would disappear and Betelgeuse would, or Orion would lose his shoulder.
Oh.
I got all excited thinking that Betelgeuse was about to go supernova. I'd certainly never seen a star change magnitude over the course of several months. You know what? Betelgeuse did not go supernova. Its brightness returned. What ended up happening is the star was just ejecting huge columns of gas through what we call stellar winds, but the gas would immediately cool down in space, and the cold clumps of gas were blocking light from the star, and that was causing its magnitude to drop. Basically, it was related to this problem. When stars are red giants, it's easier to blast stuff off the surface than it is when they are compact. Did they ask for an explanation? How did they word that question?
They asked if how the result helps to account for the fact that red giants have stellar winds.
All right, so let's add one sentence, no more. We'll just say the lower escape velocity of red giants explains explains how they can eject, and the term is called stellar winds. That's the new term for you, how they can eject stellar winds and eventually puff out into a planetary nebula. That's the end state of a star such as our sun. 2 down, 3 to go. I can almost taste my breakfast sandwich.
Stellar winds eventually puff out into planetary.
Vladimir, have you got them questions up?
It's 40, 50. Yeah, I got it.
I'm erasing. You got this, right, buddy?
Yeah.
What's it ask?
Roasting the Earth. Nice. That's the good part. Love
Yeah,
love that. During its final days as a red giant, the sun will reach a peak luminosity of about 3,000
solar
luminosities.
Okay.
Earth will therefore absorb about 3,000 times as much solar energy as it does now. And it will need to radiate 3,000 times as much thermal energy to keep its surface temperature in balance. Estimate the temperature Earth's surface will need to attain in order to radiate that much thermal energy. You will need to use the formula for emitted power per unit area in Mathematical Insight 15.5.
That's the Stefan Boltzmann Law. The Stefan Boltzmann Law tells us how bright a glowy hot object is based on its temperature. It's sigma t to the fourth, right? Light output is the Stefan Boltzmann constant times the fourth power of temperature. Vladimir, being so good at math and knowing that the Stefan Boltzmann constant is a mere number, 6 times 10 to the minus 8 watts per meter squared per Kelvin to the fourth. If I want to know how hot the Earth is going to be, I'm going to need to know what property?
Oh, the brightness of the sun by that time.
Well, we have the brightness of the sun. It's 3,000 times its current luminosity. But there's an equilibrium argument here that you need to work through with me. If the Earth is absorbing 3 times as much radiation from the sun, or sorry, 3,000 times as much radiation from the sun, it needs to re-radiate that energy back into space. Otherwise, Earth would keep gathering energy from the sun, and it would be a little energy absorbing machine, which can't work by the conservation of energy. What we need to do is figure out the brightness on Earth, because the brightness that Earth receives should be equal to the brightness that the Earth re-emits. Did that make any sense?
Yeah.
If I'm getting X amount of sunlight from the sun, Earth will warm up and it'll eventually have to re-radiate. This is an argument about thermal equilibrium. Try to imagine that wasn't true and you won't like the results. If Earth absorbs energy from the sun, but it ends up emitting less, where's that extra energy going? Down into the Earth? I don't fucking think so. The Earth doesn't destroy energy. How about the Earth emits more energy than it receives from the sun? That also doesn't work. There's no fusion bomb in there. Where is it going to get that energy? Whatever light Earth absorbs from the sun, Earth must re-radiate back into space in order to be in energy equilibrium. So let's calculate the brightness of a 3,000 solar luminosity sun on Earth. So the brightness of the sun on Earth will be 3,000 times the luminosity of the sun over 4 pi. This is the inverse square law, right?
But that problem is actually more complicated because would the distance between sun and Earth be still 1 AU? It wouldn't be, right?
Fine, you got me. No, it wouldn't be. And this problem would be more complicated. And if we were going to do it right, the way we would in a 300 or 400 level class, we'd have to do calculus on the radiation field from a much larger growing sphere. But luckily, I can make you do that. And by the way, the answer is going to come out to be about the same either way. Okay.
What? Okay. Damn.
I can't use these units. I need watts in square meters. Do you remember what 1 AU is in square meters?
Square meters?
Not 1 AU.
150 million meters.
150 million kilometers.
Kilometers. 150 billion meters then.
All right. Now the luminosity of the sun is 4 times 10 to the 26 watts. Oh, by the way, can I tell you another reason why we can still use 1 AU, Vladimir?
Why?
Because the radiation is ultimately going to be spread out over a sphere of 1 AU, whether the radius of the star is big or not. According to the inverse square law, it's the same wattage, but it's going to be spread out over a sphere 1 AU in radius. Does that sort of make sense?
Yeah, sort of makes sense.
It doesn't matter if that's a point particle or a big fat sphere. As long as the radius of the sun is less than 1 AU, which it should be, or close to it, then the brightness will be spread out over the sphere in the same way. I could explain that, but I don't feel like it, okay? 4 times pi times 150 billion meters squared. Okay, tell me the brightness of the sun on Earth. Ow. What a wonky eye. I think I got dry erase marker in my eye.
I once got gasoline in my eye.
How'd that feel?
Not great, but I didn't go blind. It was fine.
You know, one of my favorite Instagram troll pages is called Look at This Russian, and it's just Russian people doing crazy shit. That's pretty awesome. So Vladimir, if you've never indulged, you really should. You really should indulge in that Instagram page. It's just hours of fun, little video clips.
Wait, what is it again?
I think it's called Look at This Russian. Just look it up sometime. You'll get a chuckle. Got to teach these kids about memes and stuff, you know? All right, what's my brightness? I'm dying over here. My breakfast sandwich is it's not getting any warmer. I don't want the sun to turn to a red giant before I
Yeah,
get
it
to.
radiates energy. Your sandwich cannot have fusion.
I know.
So I recalculated it twice and got the same answer. So it should
What is
be correct.
It should be.
So 4 millions.
Wait.
Oh wait, what is
3,
this?
4 millions. I don't understand that.
I got 4
It's
million.
3,000 times.
I got 4
400
million too.
velocity. What'd you get?
Yeah,
4.2 million, right?
yeah. It seems a lot.
What are the units?
Watts per square meter.
Okay, so that means that Earth must have to re-radiate 4 million watts per square meter, right?
Yeah.
Earth is glowing. I'm going to say English that doesn't make any sense. Earth is glowing this, okay? Earth has to be glowing this back into space. Okay, so Vladimir, why don't you show us how you use your superior algebra skills and solve the Stefan Boltzmann law for temperature?
Okay, so B over sigma
Correct.
equal the fourth root of that.
The fourth root of the brightness over the Stefan Boltzmann constant. So we have the fourth root of 4.2 million watts per square meter divided by 6 times 10 to the negative 8 watts per meter squared per Kelvin to the fourth. Punch that up for me.
What is this?
And I'm going to look up an interesting factoid.
Wow, is it 2,900 kelvins?
Yeah. So 2,900 Kelvin. What do you think about that, Vladimir?
I think we would probably have a nice I don't know, time bathing, maybe like in sauna.
Look, I just looked up while you guys were calculating. I went to the internet. Most of the Earth's surface is covered in granite. The melting point of granite is 1,300 degrees Celsius.
Tough. So basically the mountains themselves will melt.
Yeah, the entire surface of the Earth will be molten. The atmosphere will
times.
boil away. There'll be no more oceans, and it'll basically be a lava ball. Yeah, our planet, when the sun turns into a red giant, will become lava.
Like the good old days.
Like the good old days when it formed. It formed as a lava ball. It will return to a lava ball. We got to get off the planet before that happens. Or whatever hyper intelligent robot dragonflies that we evolve into.
Yeah, I feel like humanity might kill itself before the sun dies out. That is a possibility.
Actually, the best thing that could happen is that robots will just take over and replace us.
Why is it the best thing?
Because robots have more self-control.
Are there enough resources to create robots to, like, unless you dismantle everything that we already have? Like, and besides that, there's also trash. Like, the planet will be inhabitable. I mean, but I mean, we're talking about robots that don't even exist.
Yeah, I mean, like, Homo sapiens have only existed for 2 million years. If this isn't happening for 5 billion years, we can't stay human forever.
Wait,
Evolution
2
is a
million
river.
years?
Huh?
You
Yeah.
mean the
Just
modern Cro-Magnons?
Well, I don't know about Homo erectus or any of that shit. You got to talk to your bio professor, but Homo erectus is maybe 100 million years.
No. The very modern human is like no older than 150,000 years.
Well, I thought 1 to 2 million for Homo sapiens.
I
How
don't think so.
old is Homo sapiens? I don't. Oh, damn. You're right. Sorry, I must be thinking of something else. So it's 200,000 years.
Very recent.
Wow. So we can't stay humans forever, right? We're going to evolve into something else. Now, one idea is we could evolve into hyper-intelligent mosquitoes or dragonflies. But I think a cool idea is that we'll just make robots that are smarter than us and more ethical than us. And then those robots will carry on the legacy of going to outer space. We'll make a race of machine people to populate the cosmos. I don't know. I'm just riffing with you guys. Let's move on to another problem. 3 down.
Though, like, when you mentioned the Dyson sphere, like, it'd be cool, but there's no way you can ever collect enough whatever materials you need to make the Dyson sphere.
Provided it's sufficiently thin in thickness, you could make a Dyson sphere out of any amount of material, provided it's sufficiently thin, right?
Yeah, but like sufficiently thin, but
you guys have all this, right? I'm erasing. All right. Okay, Mateus, why don't you hit us with some 51?
All right, number 51, Supernova Beetlejuice.
Oh, cool. We were just talking about this.
Yes. The distance of the red supergiant Beetlejuice is approximately 600 light years. If it were to explode as a supernova, it would be one of the brightest stars in the sky. Right now, the brightest star other than the sun is Sirius, with a luminosity of 26
Solar luminosity.
sun luminosity. Yeah, solar luminosity,
Solar
that's it.
luminosities.
And a distance of 1.6 light years. How much brighter than Sirius would the...
8.6 light years to Sirius, right?
Oh, I'm sorry. Yes, that's it. How much brighter than Sirius would the Betelgeuse supernova be in our sky if it reached a maximum luminosity of 10 to the 10 solar luminosities?
Okay. This is obviously a question about the inverse square law, right? So here's Betelgeuse going supernova, producing a shitload of light in all directions. We are 600 light years away on Earth. And that luminosity has to be spread over some distance d. And then we're going to compare it to the star Sirius, one of the brightest stars in our sky, 8.6 light years away. Let's do this Slick Rick style. If the inverse square law is brightness is luminosity over 4 pi d squared, we could calculate. We could first calculate the brightness of Betelgeuse. Then we could calculate the brightness of Sirius. Well, this is supernova Betelgeuse, I might add. And then we could divide them. But wouldn't it be cooler if we could divide them algebraically? That way we can get rid of the 4 pi's and save some time. Let's write this out algebra style, which is the slick way to do this. The brightness of the supernova as a ratio of the brightness to Sirius is the luminosity of the supernova over 4 pi, the distance to Betelgeuse squared, divided by the luminosity of Sirius over 4 pi distance to Sirius squared. Now, I intentionally set this up for maximum fuckery so that you guys would have to think about how to cancel out common terms there. I happen to know that 3 out of 2 people are bad at fractions, and that includes CCRI students, okay? So help me reduce this to the most elegant form possible. I want to see how far you guys can go. First, let's cancel out some common terms. What can we cancel out?
4 pi.
4 pi's die. Fine. Now, Vladimir, how should you arrange it for maximum elegance? Let's see if you can handle this. The brightness of the supernova over the brightness of Sirius, that's SUP, S-U-P for supernova. How do you want to arrange that, Vladimir or Mateus? We're going to want a common fraction.
I mean, yeah, I'm thinking, what do you want saying the most elegant? I have
I'm leaving
L
that.
soup.
I want to see if what you think is the most elegant is what I think is the most elegant. I suspect I could go 1 degree of elegance beyond you, but I'm not sure.
Yeah, perhaps. So I'm just looking at it and thinking what else I can do with it.
What do you have now? What do you have now? Tell me what you have now.
I have L soup times D squared, sir. Sir is Sirius.
Okay. What else?
Over L Sirius times D squared Beetlejuice.
Nice. You are almost as elegant as me.
Yeah,
but I
so
can make it go 1 more degree of elegance. You want to know how you get that extra degree of element? You factor out the square, so it's just the ratio of luminosities and distances. So the way I would write it, I have to get rid of a little bit of this, okay? I would write it as the ratio of the luminosity of the supernova over Sirius times the distance to Sirius over the distance to Betelgeuse squared. And why do I think that's 1 degree more elegant? Because now I can just quickly take the ratios, square it, and be done. It's the minimum amount of BS, right? So the ratio of the brightness of the supernova to the brightness of Sirius will be a factor of 10 to the 10 over 26 times 8.6 over 600 squared.
wait, 10 to the 10, to punch it into the calculator, it's 1 to the 10, right?
Very 1 EXP10. I was going to see if you got, I punched it in because I was worried that you guys were going to botch that. You punched that into your calculator 1 EXP10. That was a little trap that I laid for you, and you avoided it. So what's the answer?
Um, 79,000.
How about 80,000? Oh,
Yeah.
Okay, fine, whatever. It's approximately, I mean, you're right, to 2 sig figs, to 1 sig figs, it's 80,000 times
More luminous? Oh, bright. Yeah, brighter. Not luminous.
because we're thinking about it as humans watching it. Brighter than Sirius. So think about this, Vladimir. Let's go back to that picture because I actually think Sirius was in that picture. Box that, that's your answer. Shoot. Sirius is just off to the left. Hold on. I've definitely seen a picture that included Orion and Sirius before. Excuse me. Ah, this. You guys aren't seeing this, are you?
No.
I forgot to share my screen. Sorry. Can you see that?
Yeah.
Okay, so this is
So
a
the
photograph.
green
But there's
thing is
There's Orion, which you guys have obviously seen before. Sirius, the brightest star in the sky, is called the dog star. There are two dogs that follow Orion as he marches from east to west across the sky at night. Sorry, from rise in the east. Yeah, from east to west. Sorry. Okay, so Sirius is part of Canis Minor. That's the big dog. Procyon is, sorry, Canis Major is the big dog. Canis Minor is the little dog, and that's the star Procyon. But this star Sirius for years has been, for thousands of years, has been known as the dog star. It's the brightest star in the sky. When this little puppy goes supernova, it will be 80,000 times brighter than that star. You will, as I mentioned before, be able to see it during the day.
but that's not gonna happen anytime soon, is it?
Well, the problem is it's at the end of it's a high mass star at the end of its red giant life. So it could happen tomorrow.
But we will see it 600 years later.
Right. In fact, it could have actually happened 300 years ago, and we're waiting the next 300 years for the light to get to us. It would be nice if in our own lifetimes we could watch that puppy pop. That would probably freak everyone out. Be a good day to be an astronomer because we'd get lots of speaking engagements or something. I don't know.
I mean, imagine just
I'm trying
how
to
many
figure out how to
planets-
capitalize off of Beetlejuice going supernova. That's what I want to do. I need to make some money off this stuff, guys.
Yeah, and then maybe you will conserve enough money to buy that 1 meter telescope.
Yes. Now that would be a scheme worthy of the ages. The day the astronomer cheated people out of money and exploited the supernova so that he could buy himself a fancy telescope. I'd like that to be in my legacy. We'll see. Okay, we got one more problem, 54, and then I can eat my breakfast sandwich.
Wait, is your breakfast?
Well, breakfast is relative. Just, it's like time dilation and stuff. You don't know who's coming or going or what time I'm waking up. Anyways.
I mean,
So,
I'm not even gonna
listen,
say
Vladimir,
what
when I was in graduate school, there was a bumper sticker that one of the kids had on his office wall, and it said this: astronomers stay up all night. I didn't go into this business because I like waking up early, right? Vladimir, why don't you read us number 54?
Algol orbital separation.
This is what's known as the Algol Paradox, and it's about a binary star.
The Algol binary system consists of a 3.7 solar mass star and 0.8 measly solar mass star with an orbital period of 2.87 days. Use Newton's version of Kepler's third law to calculate the orbital separation of the system. How does that separation compare with the typical size of a red giant star?
Okay. To do this problem quickly and elegantly, I don't know if you guys remember this from the recording, but we're going to use the kiddie edition of Newton's version of Kepler's third law. So I've nicknamed this formula NK3 kiddie edition. It uses Keplerian units. The total mass of the system in solar mass units is a cubed over p squared. Let's think about the Keplerian units. A must be measured in astronomical units. P must be measured in years. This is going to work out nice because we already have our masses in solar mass units. What we should start off by doing is converting 2.87 days to years. Mateus, that sounds like a you job. Help me convert 2.87 days into years.
All right, so we're gonna do, I mean,
Just set up
1
your-
year on top and
Let's do
300.
units first. Sure.
Okay, so what are we doing? We are converting it to years, right?
Yeah.
Okay, so can I do that? Can I do the 1 day in the bottom and 365? No, 365 days, 1 year on top.
Yeah, I like to put the units in first so we don't make mistakes like that. So
Oh, sorry. So days in the bottom and year on top.
now you can give me the numbers.
All right, so 365 days, 1 year.
Okay. So punch that up and give me 3 sig figs.
.86 times 10 to the minus 3. I'm sorry, I'm so bad at math terminology.
That sounds good. 7.86 times 10 to the minus 3 years. Okay. Vladimir, you've got the good algebra skills, right? Help us solve for A in one shot.
Cube root of combined mass times p squared.
Nice. So that's something we can handle because we will have the cubed root of 3.7 plus 0.8 in parentheses times 7.86 times 10 to the minus 3 years squared. Why don't you see if you can all punch that up? I got something. What'd you get?
I got 1.9.
No.
No, I got it wrong. I didn't do the cubic root. I did square.
Okay.
Me too. Oh, okay. I got 2 point.
No.
So 266? No. Okay.
1 sig fig.
1. I got 1.5.
All right. Y'all fired. You're not on my astronaut team. Okay. Let's watch and learn how to do this right. Watch and learn. Okay. Give me some juice.
Oh, 0.065. Okay.
Fine. But hold on, just for the benefit of everyone else. Okay.
I cubed it. Okay, never mind.
3.7 plus 0.8. I'm going to hit equals, that's the sum, 4.5 times 7.86 exp negative 3. Now I'm going to square that, bada boom. Hit equals to do the inside. Shift cube root 0.07. What are my units though?
So that would be year. AUs.
Very good. Okay, but even though this is our answer for our separation, there's something else that you guys need to think about. Let's convert this to solar radii. And Mateus, I'm going to pester you for more dimensional analysis, okay? I'm going to have to erase a little bit of stuff up here. Mateus, you've got a separation of 0.07 AU. I'll give you a hint. It's going to take you 2 division bars to get to units of solar radii. Help me fill in the units here.
Maybe from, I know AU is longer than kilometers, but maybe from AU to kilometers to then.
Because we know that conversion factor.
Yes.
And then what will the next one be?
Kilometers to solar radii.
And that's good because we have a conversion. We know the, I remember them. Let's see if you remember them. So 1 AU is how many kilometers?
I don't remember.
Vladimir remembers. How many kilometers in 1 AU?
150 million kilometers.
Do any of you remember, we talked about it in today's lecture. How many kilometers is the radius of the sun?
7 times 10 to the 5th.
Very good. Or 700,000 kilometers. Okay. So these stars are separated by 7/100ths of an AU. How many solar radii is that?
Wait, can we do this without calculators? Is that
Yeah, but I want to eat my breakfast sandwich. Just punch it up.
15?
Does that seem interesting to you?
Wait, why?
Why? This is a binary star. 2 stars, probably main sequence stars, separated by 15 times the radius of the sun. What happens when that guy goes red giant?
It will probably gobble up the smaller.
This will actually turn into a rotating peanut of a star. This is what they call, so here's the point. The point is, but typical red giants have radii of 100 solar radii. So when one of those stars begins to go red giant, it'll actually start to absorb the other star. It might swallow it, Vladimir, or the two might become this wacky rotating peanut that swap plasma back and forth. And this is known in astronomy as a high mass contact. Sometimes they call them high mass transfer binaries, HMXBs. Astronomers love stupid acronyms for things, so HMXBs. It's a high mass contact binary, but it's kind of cool. We believe that many binaries actually will start to absorb each other, and when they pass plasma back and forth, it can actually change their spectral types and the type of fusion that go on in their cores. For instance, this will go from, basically this will become a 4 solar mass star, or at least a rotating peanut star or something. It'll probably be pretty cool if you could watch that happen.
Oh. So it will kind of pulsate as well, like returning plasma from one point to another.
Yeah, they think that sometimes, depending on where remember, so what's one of the reasons why they can pass it back and forth, Vladimir, is we learned in a previous class that as the radius of the star expands, it also loses and lowers its escape velocity. So we think that the star might expand to a point where it passes over the gravitational equilibrium, and then weirdly, plasma will spill from the larger star down onto the smaller one. But now the smaller one will grow to like 2 solar masses, and that will shrink to 1.7. So this will start undergoing faster nuclear fusion and have a shorter lifespan. Then it turns into a red giant and it passes the thing back and forth. And it's kind of like, it's like a game of catch with balls of the whole thing can get really buggy, and trying to model it is a very interesting scenario. High mass transfer binaries. Such things exist. And the Algol paradox, the paradox was, how can two stars be separated by less than the typical radius of a red giant? That's the nature of the paradox. Because I believe they suspect that one of the stars in Algol actually was in a subgiant phase or something. In fact, this is I really should know more about this, but if I type Algol star. Oh, wow, it's actually a 3-star system.
Oh, trinary.
I wanted to see what the spectral type and radii of these guys were, if it would tell us.
Wait, so the gravitational
What were you going to say, Vladimir?
I need a vocabulary word. Hold on a second. Oh, okay, there you go.
No. The more massive component, Algol AA1, is still on the main sequence. The less massive one is actually a subgiant star, so it's turning into a red giant, but it's at a later evolutionary stage, which is weird because it probably means that these guys formed at the same time. The more massive star should have run out of hydrogen fusion sooner, right? The paradox can be solved by mass transfer. When the more massive star became a subgiant, it filled its Roche lobe and the mass was transferred over to the other star, which is still in the main sequence. And so there's like some gas flow between the two stars. It's very cool. You can actually there are ways to model and measure it. Anyway.
So the gravitational interaction between 3 bodies of equal mass is unpredictable.
That's what's known as the 3-body problem in astronomy. And there are no solutions in general, except you can have some that are stable, Vladimir. Does everyone have this?
Yes.
I'm going to stop this video in 1 sec. But to answer your question about trinary star systems, they are stable in the following configuration. In the case of Algol, you have 2 stars orbiting around some common center of mass.
And then there's the dirt bag.
A little dirt bag, right? And the dirt bag orbits around the other 2 as if they were a single star. That is a stable solution to the 3-body problem. Usually, if you have 3 stars of equal mass separated by the same distance, usually 1 or 2 of the members end up getting ejected over time. But there are other solutions too. You could have a dirt bag around one of them, right? And then by the other 2, it's almost acts like a planet or something. So there are stable, like in the case of Alpha Centauri A and B are about the same mass as the sun, but Proxima Centauri is the dirt bag that has a much wider orbit, so it's stable over long periods of time. Okay, I enjoyed doing that problem assignment with you guys. I'm glad I powered through it. It's time for me to eat my breakfast sandwich. Next week, we're supposed to go into stellar death, but we have a whole extra week. And that's kind of cool because I can do a bunch of different things with that week. We could learn about general relativity, but we might actually, for once, actually get to learn and talk about galaxies. This class is supposed to be called Stars and Galaxies, but over later years, as I spent more time on it, it kind of just turned into stars with allusions to galaxies. It would be cool. It would be cool. It would be cool if we could actually include some lectures on galaxy stuff. That would be nice.
And quasars, because I read the class description, it was like quasars and nebulas and this and that. We never got to quasars.
I was just trying to get you $550. Don't hold it against me, all right? By the way,
that's kind of the reason why I took astronomy 1020 instead of 10.
Turns out you were just going to learn Newton's version of Kepler's third law. Psych.
Get bamboozled for money.
All right. No, we'll do that last week. We're just going to have some fun. That's the plan. Okay. We're going to have some fun that last week. And keep thinking about the final exam, whether you want to take it or you want to double your midterm grade. All right. Okay. I'm going to stop the video. I'm going to eat my breakfast sandwich. I'll see you guys on Tuesday. Okay.
See ya.
Get those home.
Guess what? I'm gonna go get my vaccine.
Yes, I've got mine scheduled for tomorrow. I'm very excited about that. Mine's scheduled for tomorrow. So let's get back and let's get back out to the telescope. Okay, bye guys.